Hi, my name is Manish Gupta, and in this video, I'm going to talk about FastGen, which is a method for adaptive key-value cache compression for large language models. Okay, this paper was an outstanding paper at ICLR 2024. So let's get started. Large language models need to retain key-value caches so that they can compute attention for the next few tokens, right? So, or rather for the current token generation, if you want to compute the attention score, which is basically based on softmax of QK transpose, you need to basically retain key values of all the previous positions or all the previous tokens. Now, for very long generations, one way to really manage this cache is to offload some part of this cache to CPU. However, because of limited PCIe GPU CPU bandwidth, this kind of offloading to CPU makes it super slow. What can you do in these cases? So one of the methods that this paper proposes is called as adaptive key value cache compression, which basically focuses on different kind of compression for every head in every layer, right? Uh, when it comes to basically generating an output from a large language model, the input comprises of two main things. One is basically the prompt. The process comprises of two main things. There is a prompt, which is the input, along with the task description, maybe a few short examples, and also the current problems input in that sense, right? And then there is a generation phase, right, where tokens are generated one by one. Now, when it comes to key value caching, essentially the key value caching can also be divided into two phases. The first phase can be called as prompt encoding phase, where whatever you have given in the input is basically encoded and stored in the key value cache. And then there is a token generation phase where you are generating token one by one. So as you generate the first token, its key values across all layers, all heads also need to be added to the key value cache. So if you're generating too many tokens, the cache size keeps on increasing. That's the point, right? So in this paper, what they propose is to sort of profile how these different heads behave based on the prompt encoding phase. In fact, their main observation is that different heads actually focus on different kinds of tokens. For example, some heads may be really focusing only on special tokens like the separated token or the CLS token or the start of the sequence token, instruction token, and so on, right? While there are some heads, as you can see, which basically just focus on, punctuations. So maybe they're just focusing on these colons and dots and question marks and so on. You can see in this example as well, right? Some heads are just focusing on these, special tokens, while some heads are focusing on punctuation tokens. Some heads basically, are column sparse in that senses. They're focusing only on the latest context. So you can call them as local heads in that senses. Only focus on the local tokens, right? So, for each of these heads, there can be a different key value caching philosophy or a policy. Okay. So the idea is to basically, for a given particular sequence, you try to do the model profiling based on the prompt encoding phase. So when you are encoding the prompt, after you've just finished the prompt encoding, and you're just starting with the first token generation, maybe for the first token generation, you don't optimize anything. But as soon as the first one or two tokens are generated, you would have finished profiling. What does profiling mean? Profiling basically means figuring out for every head in every layer what kind of head it is. Is it a special token kind of head? Is it a punctuation kind of head? Is it a local context, focusing head, and so on? Okay. In fact, more formally, the idea about model profiling is to pick an optimal policy for every head in every layer, such that that policy can help recover the entire attention map, which is basically this softmax of QK transpose, with a recover ratio of t, where this ratio should be very high, something like 90-95%, something like that, with minimum memory cost. Okay. For example, if you basically just keep the punctuation marks or the punctuation based tokens for this head, can it recover like 95% of the attention map for this head? If yes, then there is no point keeping anything else, because punctuation marks typically would consume the minimum memory cost in that sense. Okay. So accordingly, basically, now, which kind of policies can you select, right? So therefore, in this paper, they basically propose multiple compression strategies or compression policies. Okay. The first one is special tokens. We already talked about it. Retain only, start of sequence or end of sequence or instruction token kind of, key value cache for those tokens, right? Retain key punct is punctuation. So retain, key value cache only for punctuation tokens like full stop, colon, question mark, and so on, right? Local policy basically means that you retain, only key value caches of local tokens or other, tokens up to a particular distance from the current token which is being generated, right? You evict all long range contexts. So you don't keep long range contexts at all, right? So retain tokens only up to a distance, a particular distance threshold. They measure the threshold in terms of ratio of local context length to sequence length, and they keep the threshold as 30%. Okay. The other policy is frequency. So certain tokens may be accessed by a lot of future tokens. So therefore, what you do is to ask for every token how many future tokens are accessing it, right? And then you keep the most frequent tokens. So in their particular case, they keep a budget of 30% again, which basically means that 30% most frequent accessed tokens are retained. Others are basically just evicted. Key value caches for other tokens are just evicted. Okay. The last policy is full policy, which basically means this is the default policy. So the point is that if none of the other policies or strategies are able to retain at least 95% of your attention map, then you basically just fall back to the full policy. So these are heads which are basically, focusing on almost everything, more like global heads in that senses. So then you retain key value caches for all tokens for these particular heads. Okay. So you see, I mean, while these policies individually may make sense, they may individually not be very effective. And therefore, what these folks did was to combine policies. So they said that their policy set is not going to be these individual ones, but policies which contain these 5 things. Obviously, it could be the default policy is full, but then you can also just store the special tokens, or you can store special plus punctuation tokens, or you can store special plus punctuation plus frequent ones, or you can actually store special plus punctuation plus frequent plus local tokens. Right? So that is that. Okay. Now, interestingly, what they observed, their entire profiling just depends on the prompt encoding phase, right? The question is that does the profiling done at prompt encoding phase also hold over the entire token generation phase, especially for long form generation, right? And their experiments actually showed that yes, profile tends to be consistent in one sequence for each head across layers. So therefore, you can just profile based on prompt encoding phase and apply it over all the tokens in the token generation phase. Okay. Now, how does their FastGen method perform? So they experimented with Llama 1 model only, right? So Llama 1, the original model, and also Llama 1, the fine-tuned model. They specifically fine-tuned the model because their method does not really work on Llama 1 chat because it uses GQA, the grouped query attention. Their method right now only works on the full, vanilla attention in that sense, the multi-head attention. Okay. They experimented with 4 different data sets, GSM 8K for math, human eval for coding, natural questions for knowledge question answering, and trivia QA for common sense reasoning on 8 800 machines. So that's the infrastructure. So you see, in the first plot, you can basically see a comparison of their method FastGen with full cache versus frequency plus local. The y-axis is F1. This particular plot is drawn, the first row is basically drawn for GSM 8K. Results for other data sets are in the paper, right? There are 4 different subplots, and these subplots basically talk about the 7 billion, 13 billion, 30 billion, and 65 billion checkpoints. What you can observe is that the F1 score is obviously going to be the highest based on the full cache, right? The full cache, right? X-axis basically here indicates the key value cache budget. So yes, I mean, the F1 score is basically going to be the same, whichever policy you use, whether you use FastGen or frequency plus local. Frequency plus local is a very, very popular baseline. I mean, people typically keep those particular heads, which are in the local context or frequently accessed in that senses. Okay. And you can see that if you retain 100% of KV cache, then sure, you would be as good as the full cache anyway. But if you look at 60%, 40%, right, you observe that the orange line is above the blue line, which basically says that the FastGen approach actually gives you better results compared to the most popularly used frequency plus local KV caching optimization approach. Okay. The same kind of results also hold when you basically look at the fine-tuned Llama 1 model. So these are results on the fine-tuned Llama 1 model averaged across all the 4 tasks. And again, results are presented for the 7 billion, 13 billion, 30 billion, and 65 billion models. Now here you see results for FastGen compared with individual policies themselves as well, frequency, local, and frequency plus local, besides full cache. Right? Full cache is clearly the best. Okay, so y-axis basically here is slightly different. It is the win rate over full cache. Okay, so if things if things work perfectly well, then the win rate over full cache will just be 50%. So that's basically perfect results in that sense, right? So now what you observe in the x-axis remains the same. So you basically can do 50% compression of your key value cache using various policies. And if you basically look at 50% compression, you observe that you see, the orange curve is always higher, whether you do 50%, 60%, 70%. Sorry, here it is like 60% to 0% compression in that sense, right? So this is the key value cache budget. So yes, for 100%, you see the FastGen is able to get a win rate which is the same as the full cache, and you see the orange curve is typically always above all the blue curves, all the blue baselines. Another interesting thing to observe is that, even with 50% compression, let's say for this 30 billion model, if I look at this 30 billion model, 50% cache compressed FastGen, so 50% cache compressed FastGen, this guy is actually better compared to even a 15% compressed baselines. Okay, so if you compare, 85% key value cache budget basically means these are 15% compressed baselines. So even 15% compression does not really give them as much win rate as, a 50% compressed FastGen method. Okay, so that basically this for a 30 billion parameter model. Of course, for a 65 billion parameter model, you observe that even a 40% or a 60% compressed model, with just a 40% FastGen budget, is actually way better compared to any of these 80% compressed baseline models. Okay, or the 20% compressed baseline models. Okay, so that's that. Now, this win rate and end-to-end accuracy is great, but how much memory actually does it save? This is all theoretical, right? So there's key value cache compression and so on. How much memory does it really save, right? So they experimented with these memory budgets on A100 machine for different model sizes, and you can observe that if you kept the full KV cache for a 7 billion parameter model, it takes 4.3 GB. But with FastGen, if you basically use with a policy of 95% attention map retaining, it basically gives you a 2.6 GB FastGen KV cache with a win rate of about 37.7%. Sure, if you wanted a win rate of about 47%, you can still compress 4.3 GB to 3.6 GB while retaining 98% of the attention, a 17% pruning ratio, while retaining 98% of the attention map and 47% of the win rate. Okay, so that's that. Now, how does this help with latency? Does it really improve latency also? So, well, it turns out that it does improve latency also significantly. So they experimented with batch size of 1, 2, and 8, right? And they experimented with different prompt lengths and generation lengths. So basically, there is 32 prompt length and 512 generation length, and so on. There could also be 512 prompt length and 512 generation length, or 4096 prompt length, 4096 generation length, and so on. Okay. They experimented, with multiple baselines. So the first row is basically Hugging Face accelerate baseline. Accelerate is one of the most popular methods to train, to infer from the models very efficiently. Right. So they used Hugging Face accelerate. Then they use deep speed. Deep speeds, optimizations, kernel optimizations also help you, obtain very quick inferences. Further, they experimented with FastGen, which is implemented on top of deep speed. So a fair comparison is to really compare FastGen with respect to deep speed, right? And what do you observe? You observe that you get some latency benefits across the board, right? Now, the latency benefits obviously increase when your generation length increases compared to the prompt length. So if you have a prompt length which is 32, and generation length increases, your improvement, your speed up over deep speed also increases. And this is obvious because FastGen applies only for the token in the token generation phase. In the prompt encoding phase, you're not doing FastGen because you're not yet done model profiling in that sense. Okay. So the same thing holds for batch size 2 and 8 as well. As your generation length increases, the gains that you can obtain in terms of latency also increase. The speed up basically also increases. Okay. So in short, in this video, I talked about FastGen, which is a method to improve inference efficiency of large language models with no visible quality loss by using lightweight model profiling to actually figure out for every particular head in every layer of the model as to what is the right policy to use in terms of KV caching for all the tokens in the input, right? So basically it uses adaptive key value caching. The best part about this model or this way of doing things is that it is not resource intensive and doesn't, or rather, it does not involve any resource intensive fine tuning or retraining. It is totally inference time only. Okay. However, one negative part of this is that it does not work for GQA as of now. It sort of needs special kernel design, which works with deep speed. So, if you're working with, let's say, Hugging Face Accelerate, implementing this on top of Hugging Face Accelerate will be some more work. That's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.